I want to prove something to you. So to do so, I want to take some random shaped object. I don't care what it looks like, just something, a meteor spinning in space, okay? Something random. I'm going to choose an axis of rotation somewhere in the middle of the object, but not, offset a little bit. And we'll say the object is spinning with an angular speed like that. Everybody understand? Just some random object spinning in space. I want to pick 4 pieces of the object. Look, some of you are never impressed with anything, except for yourself. Some of you are very impressed with yourselves. You should probably reconsider that. You're not as entertaining as you think. I mean, some of you are funny, but that's not I don't think that's what you've been going for. That's why I think you should reevaluate how impressed you are with yourself. And I don't mean this mean. I just mean this in straightforward, honest fashion, that nothing impresses you if it's probably not on TikTok. I want to prove something to you because I believe in evidence. And I believe that by building things up from evidence, we build foundations of knowledge that move us forward as a community. That you shouldn't just buy into what people tell you. At the same time, you shouldn't constantly throw things out of hat because you just don't feel like working hard at understanding it. Now, I want to show you something because this is something that is easy to understand. You can parcel this out very easily. So I've picked 4 different parts of this object. And I'm going to label them M1, M2, M3, and M4. All different parts of the object. This object is spinning, so each of those pieces is moving. If you'll recall, first semester, kinetic energy is 1/2 mv squared. So each of these pieces of the whole thing, but these are 4 pieces, each of these pieces has its own amount of kinetic energy. Piece 1 would be 1/2 m1 v1 squared. And piece 2 would be 1/2 m2 v2 squared. And piece 3, 1/2 m3 v3 squared. And piece 4, 1/2 m4 v4 squared. 4 individual pieces of the object. Now, I want to consider piece 1 for a minute. If the object is spinning, then piece 1 has a velocity that is probably, use a different arrow, probably something like that. It's the slowest of all the pieces, and that would be its velocity, v1. But all of these pieces are part of a bigger object, and that bigger object has velocity omega. So I know from what we studied already that there is a way to deal with the distance from the axis of rotation to where that piece is, and that my velocity would be tangent to that circle. In fact, I know more than that. I know that v1 would be equal to omega times r1. Right? That's what we've learned so far for rotational kinematics. In fact, let's go on. Piece M2. It's got a little more velocity, so it's a little further away. Right? This is V2, which is going to be omega times R2. Now, piece 3, it's way out there. I think this is the fastest piece. So it's got the longest value of R. So it's going it's going faster than probably all the other ones. Right? Because it's going to be V3 equals omega times R3, and R3 is the longest. And of course, R4, somewhere in the middle. I think it's a little faster than 2 and 1. We'll say V4 equals omega times R4. I bring this up because each one of these pieces has its own kinetic energy, but I could write all those kinetic energies instead of in terms of v, which is different for all of them, I could write it in terms of omega, which is the same for all of them. So let's try that. I'll get 1/2 m1 omega times r1 squared and 1/2 m2 omega times r2 squared and 1/2 m3 omega times r3 squared and 1/2 m4 omega times r4 squared. Now, if I could do this for every piece of the object, this would be the kinetic energy of the object as it spins. I haven't talked about that yet, but obviously kinetic energy is motion, period. If every piece of this object has kinetic energy because the object is spinning, wouldn't we be able to say through the transitive property that the object has kinetic energy even though it's not changing location? It would have to be, because the pieces of the object have kinetic energy. So let's add all these together. But I'm going to notice that I have a 1/2 in all of them. So I'm going to pull the 1/2 out front. So K total, 1/2 out in front. I'm also going to notice that all of them have an omega that is squared in them. Do you guys all see that? So I'm going to pull out the omega squared, put it to the right. In the middle, I'm going to have m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Do you see where this is going? Do you know what mr squared represents? It's the moment of inertia of a point mass. If I added this up for every piece of mass of the object, don't you realize that I would just be adding up the moment of inertia of the entire object, right? Rotational kinetic energy is 1/2 I omega squared. But we've done more than just do that. We've also proved where I comes from. We've proved why I is mr squared. Why all of the things that have a moment of inertia have an inertia that's based on the square of the distance away. It all boils down to kinetic energy. That kinetic energy is the reason why all of those pieces contribute so much more to the kinetic energy and therefore the inertia because they're further away. Kinetic energy is the form of energy that takes inertia into account. 1/2 m v squared. The inertia matters. And it doesn't matter as much as the velocity, which is why the further away pieces have more kinetic energy than the closer pieces. But also, at the same time this object is spinning, its center of mass could be moving through space. A football spinning, a softball spinning, a golf ball spinning, a hockey puck spinning. Its center of mass is going from one location to the other, but the object is also spinning. So an object with translational kinetic energy would be 1/2 mv squared. And if it's spinning at the same time, it would have rotational kinetic energy. This has big implication for an object that rolls. An object that rolls has both translational kinetic energy and rotational kinetic energy. So let's start with this. This is how we calculate energy for objects that rotate. 1/2 I omega squared. The thing about rolling that ramps this up a little bit is consider an object that rolls. To roll, we need something round, right? That's why we studied the hoop and the disc and the ball so much, because they're round, they can roll. Let's say that this object is rolling at omega, has radius r, mass m, and because it's rolling, and we stated that it's rolling, its center of mass has velocity v. this object has two kinetic energies. It has translational kinetic energy, but it also has rotational kinetic energy. So right away, 1/2 I omega squared plus 1/2 m v squared. Now, this is worth watching. Because it's rolling, we know that has to be true. The moment they say rolling without slipping, or even just rolling, if they don't say it's slipping, there's no indication that there'd be a reason for it to slip, then this condition has to be true. That means automatically that substitution is always in play for things that are rolling. I'm going to be able to put in V over R for the omega. If I just do a little bit of regrouping, I get I over R squared here for everything that rolls. Now, if I set this to the side for just a minute and state that, well, this is the kinetic energy of the object, the total kinetic energy. Every version of I for things that roll that was a good one. I don't know why you're holding it in. Just let it out. Just project, man. Oh, over there, away from all of your friends. Do you notice that every single version of things that roll has R squared in it? Every version. So things that are rolling are going to have some kind of value for the kinetic energy that's going to be 1/2 mv squared plus something else mv squared. Something here that's going to make its way inside that. Do you see what I'm saying? Now, the biggest thing to take into account here is things that are rolling have more energy than things that are sliding because they have two forms of energy at once, both rotational and translational kinetic energy. This is going to play a lot with all those conservation of energy problems we've done. Think of every single problem that's had conservation of energy: a marble rolling down a ramp, a disc rolling around a loop, and how the energy is now going to be different because the energy gets divided up into translational and rotational. A thing that's rolling starts at a certain height, might have the same energy as something that slides, but the rolling object has to divide its energy up into translational and rotational. Well, the object that slides doesn't. It might have to deal with friction, but we're still going to be dividing our energy. So that's going to play a big factor in how our problems are shaped. We'll stop there.